Hi all, welcome back with another video of equivalent series. Today we are going to see equivalent capacitance, right? So which comes under electric fields, equivalent capacitance, right? So first, if I recall the theory part here, for a capacitor, right? For a capacitor, let's say the capacitor is connected between A and B, right? The relevant equation is Q equals CV. Relevant equation is Q equals CV, where Q is stored charge. Q is stored charge, right? And C is capacitance, capacity or capacitance, right? And V, not the voltage, voltage difference. Voltage, or it is also called potential, voltage or potential difference. Voltage difference, right? So this is the basic equation. It runs a capacitor, right? Now let's see what happens in series and parallel combinations of capacitors. First, let's see the series combination. Series combination. See, series combination of capacitors. Series combination, right? So we know series combination is an end-to-end combination. Series combination is an end-to-end combination. Then capacitors should be connected end-to-end like this. Let's consider three capacitors of capacitances C1, C2, and C3 connected between A and B, right? Connected between A and B, right? And the equivalent should be connected to the same points A and B, and let's say the equivalent is CE, equivalent capacitance, right? So we know when it comes to stored charge in a capacitor, that is very much similar to what happens in current flows in resistors, right? So we know if there are no junctions, current is not going to be divided. Similarly, if there are no junctions, flowing charge is also not going to be divided. So therefore, same charge will be stored in each capacitor in series combination, right? A very important point. Same charge will be stored in each capacitor in series combination. So I'm going to consider the stored charge here as, say, Q, right? Stored charge here as Q, and Q. Then here also it should be same Q, right? We know according to this Q equals CV. Now Q is same, but C is different. It is given, which means definitely V is different. So let's consider these potential differences again as V1, V2, and V3, right? And this total potential difference, we know that this total can be written as what? VAB. Total can be written as VAB, right? Always build up your argument for the different quantity. Different quantity is potential difference now. So my argument is VAB equals V1 plus V2 plus V3, right? VAB equals V1 plus V2 plus V3. Then we know according to this equation, look at the board. According to this equation, Q equals CV. V is Q over C, no? V is Q over C, right? Then VAB can be written as Q over CE, right? V1 can be written as Q over C1, V2 is Q over C2, and V3 is Q over C3. Q to Q to Q to Q cancels, right? 1 over CE equals 1 over C1 plus 1 over C2 plus 1 over C3. So this is the proved equation for equivalent capacitance in series combination, right? So higher the number of capacitors in series combination, lower the equivalent capacitance, because this is a 1 over addition. This 1 over addition, right? Addition of reciprocals. So therefore, higher the number of capacitors in series combination, it lowers the capacitance, right? So just know that capacitors are acting exactly opposite way to resistors, because in resistors, when resistors are in series combination, right, equivalent is R1 plus R2 plus R3. Now in capacitors are in series combination, that is 1 over C1 plus 1 over C2 plus 1 over C3, right? So this is about the series combination. Now let's see the parallel combination. parallel combination. See what happens parallel. Okay, so let's consider these three capacitors which are in parallel combination, right? Connected between A and B. Connected between A and B, right? Let's say they are C1, C2, and C3. So equivalent should also be between A and B, say CE, right? Now we know along conducting wires, points are not going to be different. Points are same. Points are same. So therefore, if this is A, this is A. Up to here A, this is also A. If this is B, this is B, B, and B. All capacitors are connected between A and B, which means same potential difference, right? Same potential difference across all capacitors. Okay, now again, argue with the equation. According to Q equals CV, now V is same. If V is same, since C is different, Q should be different. Q should be different, right? So let's consider stored charge here as Q1, stored charge here as Q2, and stored charge here as Q3, and stored charge on the equivalent as QE, right? So build up your argument for the different quantity. Different quantity is now being the charge, right? So therefore, what we can say is QE equals Q1 plus Q2 plus Q3, right? Because always the equivalent should do the same that was done by the system before. If the total charge stored in the system is Q1 plus Q2 plus Q3, total charge should be stored on the equivalent single-handedly as Q1 plus Q2 plus Q3, right? So we know Q equals CV, right? So QE is CE VAB, Q1 is C1 VAB, Q2 is C2 VAB, and Q3 is C3 VAB. VAB cancels, right? Here we are C1 equals CE equals C1 plus C2 plus C3. Proved equation 4. Equivalent capacitance in parallel combination, right? So in parallel combination, higher the number of capacitors, higher the equivalent capacitance, right? So that's why I said, that's what I said, capacitors are behaving exactly opposite way to resistors, right? In parallel combination, resistors were one node addition, capacitors are just the addition, right? So just know those differences as well, right? Okay, so hope it's clear. If there's anything, you can add a comment to the video, then I will respond. Okay, I'm going to stop the video here, and we have one more equivalent remaining, right? So let's meet with that video again shortly, right? Okay, goodbye.